Hello, today I'm going to explain a couple of examples on variation of parameters. So here is my first example. It is from the textbook. It is 3.7.7 from the textbook. So how do we solve a non-homogeneous second order linear differential equation? So notice that now the right hand side is not zero. Well, the basic formula is that the general solution of this differential equation is going to be a particular solution of this differential equation plus the general solution of the corresponding homogeneous equation. So plus, I will write y homogeneous. So plus the general solution of the homogeneous equation. So let us first find the general solution of the homogeneous equation. Well, the homogeneous equation is the same thing, only we need to equate the right hand side to 0. So we get y double prime plus 4y prime plus 4y equals 0. This is the homogeneous equation. To solve a second order linear homogeneous differential equation, we write down the corresponding characteristic equation. R squared plus 4r plus 4 is 0. So notice that the left hand side is a complete square, right? So this is r plus 2 squared. So we have two roots. 1 and 2 are both equal to -2. And if we have a multiple root of the homogeneous equation, it means that the general solution is going to be y equals, well, the general solution of the homogeneous equation is going to be some constant c1 times e to the -2t plus some other constant times t e to the -2t. Alright, so let us denote this e to the -2t by y1 and t times e to the -2t by y2. So then, according to variation of parameters, so maybe I should clarify that in the lecture I explained variation of parameters in all the details because I wanted to prove the variation of parameters and I wanted to show you how the basic logic behind it. So how people in the 18th century came up with the idea of using variation of parameters. But of course, when you solve questions on variation of parameters, you do not really need to follow all the same steps. You just need to use the end result. And the end result in variation of parameters is that particular solution of the homogeneous equation is going to be u1 times y1 plus u2 times y2, where this u1 and u2 are now functions of t that can be calculated according to this formula. u1 is going to be minus the integral of y2 times g over the Wronskian, and u2 is going to be the integral of y1 g over the Wronskian dt. Now, what is g here? So g is the right hand side of the original differential equation, only we need to make sure that the coefficient at y double prime is 1. So notice that here the coefficient at double prime is indeed 1. So it is in the right form, which means this thing is our g. Now, what is the Wronskian? So the Wronskian is just a determinant constructed out of these solutions of the homogeneous equation and their derivatives. So the Wronskian here is the determinant of the first row here is e to the -2t and t times e to the -2t. So that is our solutions of the homogeneous equation. And the second row is their derivative. So we differentiate e to the -2t, we get -2 e to the -2t. Then t times e to the -2t, we differentiate by the product rule. So we get e to the -2t -2t e to the -2t. And this is the determinant. So we've got to do this times this. So we get e to the -4t minus 2t e to the -4t minus this times this. So we have a minus here. So minus and minus gives us plus. So it is plus 2t e to the minus 4t. As you see, they cancel out, so the Wronskian is e to the negative 4t. So which means that now we have all the ingredients for the variation of parameters. So we can write t1 is minus the integral, y2 is t times e to the minus 2t, then g is our right-hand side of our original differential equation. So this is t minus 2 times e to the minus 2t, divided by the Wronskian is e to the minus 4t dt. Alright, so all exponential functions cancel out here. So the remaining part is, well, we still have a negative sign here. So t times t to the minus 2 is t to the minus 1 dt, and t to the minus 1 is 1 over t, so its antiderivative is ln t. Well, strictly speaking, it's ln of absolute value of t, but notice that t is positive. The basic reason is that since we have a division by t here, it means that t should be either positive or negative, and, well, they chose the positive part. So it's ln t. U2 is going to be calculated according to the similar formula. So this is the antiderivative of y1. Our y1 is, where is y1? Is e to the minus 2t. Then times g. Our g is still t to the minus 2 times e to the minus 2t. Everything divided by the Wronskian, and the Wronskian is e to the minus 4t dt. So still Wronskian cancels out. So the remaining is the integral of t to the minus 2 dt, and this integral is what is minus t to the minus 1. Yeah, by the way, notice that I did not add plus c in both integrals. This is because we are looking for a particular solution of the non-homogeneous equation. So we are not looking for all possible solutions, because once we got any particular solution, all other solutions can be constructed by adding the general solution of the homogeneous equation. So at the same time, we could construct it, the general solution, by just adding plus some c1 here, plus c2 here, and solving the integrals with the additive constants. But I think it's simpler just to find one particular antiderivative and then add this to the final answer. Okay, so now the final answer is going to be y is going to be what is going to be our particular solution, so which is minus ln t, sorry, so we are going to have negative ln t times, this is u1, times y1, sorry, y1 is e to the minus 2t, plus u2, so plus our u2 is minus t to the negative 1, times y2. Our y2 is t e to the negative 2t, plus some constant c1, e to the negative 2t, plus some constant c2, times e to the times t times e to the negative 2t. Okay, so now we are almost done. So notice that t and t inverse cancels out here, and also notice that we have negative e to the minus 2t here, which should actually belong here, right? So what we got is that kind of a part of our particular solution, it turns out to be in the homogeneous, in the solution of the homogeneous equation. So maybe we should push it where it belongs. So, I mean, of course, the total expression is going to be, I mean, if we include this, it's going to be e to the minus 2t with coefficient c1 minus 1. But if c1 is an arbitrary real number, then c1 minus 1 is also an arbitrary real number, which we could denote by c1 tilde or something like that. My point being is that we don't really need this. And the final answer should be just minus ln t times e to the minus 2t plus c1 e to the minus 2t plus c2 t e to the minus 2t. This is the final answer. Well, let me write it nicer. Plus c1 e to the minus 2t plus c2 t to the minus. Yeah, and now if we had an initial value problem, then we could solve for c1 and c2 from the initial value problem.